Okay, good afternoon, ladies and gentlemen. Once again, this is Maths with Gary coming to you from the bridge of the Starship Enterprise. And as you can see, the crew has been given the day off again, just for something different. So today I want to talk to you about a method of integration that causes students a lot of trouble, and it's not that surprising because it's actually a fairly hard method of integration. But it is one that you need to learn for certain subjects. And it is method of integration by trigonometric substitution. And let me go to my file. So it's a reasonably advanced method of integration. I want to compare and contrast that with integration by U substitution, with which we're all fairly familiar. And so here's an example of integration by U substitution. We've got this integral, the integral of x times e to the 2x squared dx. Now, x is fairly close to being the derivative of 2x squared. In fact, there's only a constant difference. So if we put u equals 2x squared, then du becomes 4x dx. Now, you might be more comfortable saying, well, du dx is 4x, and therefore du is 4x dx. So in that case, we would actually be treating du dx as if it's two things. It's a small change in u divided by a small change in d. Whereas normally we consider du dx to be one thing, it's the derivative. So we can be a little bit sloppy with our notation there in that regard. Now I'm writing this as 1/4 times the integral of e to the 2x squared times 4x dx. The red bit at the back is du, and the blue bit at the front is f of u. And so we've got the integral of f of u times f of g of x times g dash of x dx. And the 1/4 out the front, of course, is to keep it the same, because if I just put in the 4 and have the integral of e to the 2x squared times 4x dx, then it's no longer the same as this. But because I can move multiplicative constants in and out of my integral sign anytime I like, this is actually the same as this. And so I haven't changed it. Well, now making those substitutions, I've got the integral of e to the u du, and of course that is e to the u, so we get 1/4 e to the u plus a constant. And I'm noting that at this point the integral has actually been done. We've done the integration, but the problem is that our answer is not in terms of x as the question was, but it is in terms of u, and so we've got to convert backwards. So we go back to 1/4 e to the 2x squared plus c. And that's our final answer. And it is in the same variable as the question was, which is pretty useful. So we wrote that in the form the integral of f of g of x dx times g dash of x. We defined the new variable u in terms of x. In other words, u is equal to some function g of x. G dash of x dx is equal to du. That's simpler than g dash of x dx. And f of g of x actually becomes f of u, which is also simpler. And so the whole integral becomes the integral of f of u du, which is a much simpler integral. If you compare this one here, the integral of f of g of x times g dash of x dx with the integral of f of u du, it's pretty clear that this one is a simpler integral, and therefore should be quite a bit easier to do. But integration by trigonometric substitution works quite differently. Have a look at this example. So we've got I equals the integral of 9 minus x squared to the power of a half, and of course that's the square root. And I could have written it as the square root. I chose to write it as a power of a half. It's the same thing. This time, instead of using a substitution of the form u equals f of x, we actually use a substitution of the form x equals some function of theta. And this time dx is equal to f dash of theta d theta, which is actually more complicated than dx. And also 9 minus x squared to the half is going to become 9 minus some function of theta squared to the half. It's all getting significantly more complicated. It's longer, it's harder. What's the point? Why? Well, the point is that we can choose this particular substitution f of theta so that we can use trigonometric identities to simplify the integral. Now, if we use the wrong substitution, it's going to stay harder. We won't be able to do it. But if we choose the right substitution, then it's going to become simpler. And this table here shows the guidelines for choosing the substitution. So I've got a column for the term that the integral involves. I've got the substitution. We've got a column for dx, and we've got a column for the identity that we'll be using. And if the integral involves a squared minus x squared, we choose x equals a sine theta. Dx is a cos theta d theta. And we use cos squared plus sine squared equals 1. If, on the other hand, the integral involves a squared plus x squared, then we use x equals a times tan theta. Now, not a tan theta, which in some computer languages would be the arctan or the inverse tangent of theta, but a times the tan of theta. Our dx, of course, is a times the sec squared of theta d theta. And the identity that we require is 1 plus tan squared equals sec squared. On the other hand, if the integral involves x squared minus a squared, then we use x equals a sec theta, dx equals a sec theta tan theta, d theta. And again, we use 1 plus tan squared equals sec squared. That makes sense. We've got these two columns here involving a tan theta and a sec theta. And so it looks like the same identity will be useful because it involves tan and sec. That makes sense. So let's apply this idea to our example and give it a shot. So we've got the integral of 9 minus x squared to the power of a half dx. And the first row of our table tells us that we should use the substitution x equals 3 sine theta. So a squared is 9 here. That pretty clearly makes a equal to 3. Dx is 3 cos theta d theta. And let me try and get this up a bit higher. And so our integral I is the integral of 9 minus 3 sine theta squared to the power of a half, or the square root if you prefer, times 3 cos theta d theta. And it's significantly more complicated. This is a much harder problem. We've made it worse. But there is hope. So I've taken this 3 out the front straight away. I've got 9 minus 9 sine squared theta to the power of a half times cos theta d theta. I've taken the 9 out. 9 to the half, or the square root of 9, is 3. And so I'll have 3 times 3, which is 9. 1 minus sine squared theta to the half times cos theta. And at this point, we're going to apply that identity. So we'll have 1 minus sine squared, of course, is cos squared, still to the power of a half, times cos theta d theta. And that will give us 9 times the integral of cos squared theta d theta. And that's a much simpler integral. If you compare that to the original, this one's easier, but it's still not trivial. Let's use another identity. So I'm going to write this as 9 times the integral of a half 1 plus cos 2 theta d theta. If that was sine squared, it would be a half 1 minus cos 2 theta. But we need to find a way to remember that. So I've taken the half out the front. We've got 9 over 2. And the integral of this is theta plus a half sine 2 theta plus a constant. Technically, of course, the plus c should really be inside these square brackets. But I'm not going to do that because then we'd have 9 over 2 times a constant. And 9 over 2 times an unknown constant is, surprise, surprise, it's an unknown constant. So I'm quite happy to just add this constant outside of the square bracket. So we've got 9 over 2 times theta plus 9 over 4 sine 2 theta plus a constant. And so now we've actually done the integral. Right, fantastic. But of course the answer is in terms of theta, not in terms of x. I've got to return to a solution in terms of x. Otherwise, I don't know what the answer is. the question was in terms of x, the answer needs to be in terms of x as well. And so we're going to use the original definition of theta and the inverse sine function. Now we said that x was equal to 3 sine theta. That means that sine theta is equal to x over 3. I'm going to cough, just hold on. That was not a signal to go to warp speed, just a cough. And so theta is the inverse sine of x over 3. So that tells me what the first term is. The second term is quite a bit harder. Sine 2 theta, I don't know anything about sine 2 theta, but I do know something about the sine of theta. Sine of 2 theta is 2 sine theta cos theta. Sine theta is x over 3, but what's cos theta? So what I'm going to do here is I'm going to construct a right triangle, and I will use the fact that sine theta is x over 3. And I'm missing an angle theta. That's not very helpful. This should be the angle theta in here. And so the sine of theta is x over 3. My apologies for that. There should definitely be a theta right there. So the sine theta is 3 over x. It's not 3 over x, it's x over 3. Using Pythagoras' theorem, I get that this side here is actually going to be the square root of 9 minus x squared. And so the cosine of theta, being this angle here, will be in fact the square root of 9 minus x squared on 3. There definitely should be a theta there. I'll tell you what, I'm actually going to pause recording and I'll put that in. Okay, so we're back live on the bridge of the Enterprise, and here is our diagram again, and this time we've got a beautiful theta right there. And so you can see that the sine of theta is x over 3, the cosine of theta is now the square root of 9 minus x squared over 3. And so we've got this, I is 9 over 2 times the inverse sine of x plus 9 over 2 times x over 3, because it was 9 over 4 times 2 sine theta cos theta, so the 2 and the 4 cancel out, leaving 9 over 2. X over 3, 9 minus x squared over 3 plus c, and of course I'm going to have 9 on the bottom, which will cancel out with this 9. And so this will be the final integral. So now that we've gone back to x, everything's finished. It's all done. And so that is a bit of a motivating look at why we use trigonometric substitution and how it's different from U substitution. Let me go back. So with U substitution, the integral collapses into a very simple integral straight away. Hopefully anyway. With integration by trigonometric substitution, it gets bigger and harder straight away. Bam! That's much worse. But by very clever use of our trigonometric identities, it becomes a smaller, simpler integral. And the key to that is this table, this list of suggestions for your substitution. You should memorize that. It's not that hard. You may find that in your assessment situations, test exams, stuff like that, that you actually get an information sheet containing this, but you may not. And so you should memorize it. How do you memorize things in mathematics? You write them out. I'm going to stop sharing this because this is one of my favorite topics to talk about. I'm a big fan of rote learning because the more you learn, the more you know. The more you know, the smarter you are. The smarter you are, the better job you can get and the more money you can get paid, and money's good. So, and I always say to my students, employers are not looking for people that can look stuff up. Anyone can do that. They're looking for people who know stuff. And so the more you know, the better placed you are in a competitive job market. So write things out. I'm a big believer in writing things by hand. Okay, there is a very powerful link between writing and remembering, and so the more you write, the more you learn. Okay, thus endeth today's lesson. So as always, enjoy maths and good luck in your study. carry on. I shall see you again. Until then, it's Captain Gary out.